Solutions. A solution is a homogeneous mixture of one or more solutes and the solvent. Homo means the same or consistent throughout. So it consists of the same relative composition throughout. So I can take one part of the liquid and another part of the liquid, and it should have relatively similar composition. The solute is the substance being dissolved. The solvent is the dissolving agent and is usually the most abundant substance in the mixture. Air is a solution of nitrogen, oxygen, argon, carbon dioxide, and so forth. What substance is the solvent in air? Nitrogen, since the majority of the gas in air is nitrogen. Sweet tea is prepared by dissolving an instant tea packet in water. Which substance is the solvent? The water. A solution of alcohol in water is prepared by adding 25 ml of water to 75 ml of alcohol. Which substance is the solute? Well, water is the solute because it's the thing that was added in lower quantity. A homogeneous mixture, a homogeneous mixture, however you'd like to pronounce it, is a mixture of two or more components whose ratio can be varied. The dissolved solute is molecular or ionic in size. Liquid or gaseous solutions can be colored or colorless and are usually transparent. The solute will not settle out of the solution. The solute can be separated from the solvent by physical means. So how a solid dissolves in water is depicted below. So this is how salt would dissolve in water. So the water molecules will surround the chloride ion and the sodium ion. And the positive ends of the water dipoles are attracted to the negatively charged ions, and the negative ends of the water dipoles are attracted to the positively charged ions. And that's what's going to surround the molecules, or the individual ions. In a solution of sodium chloride, the sodium and chloride ions are dispersed in the water. The water molecules surround the ions of sodium chloride and disperse them in solution. Electrolyte versus non-electrolyte solutions. Electrolyte solutions contain dissolved ions, which are charged particles, and therefore they conduct electricity. Non-electrolyte solutions contain dissolved molecules or neutral particles, and therefore do not conduct electricity. So electrolyte solution, they're showing salt water. In a non-electrolyte solution, they're showing sugar water. Solubility and saturation. The solubility of a compound is defined as the amount of compound, usually in grams, that dissolves in a certain amount of liquid. A saturated solution holds the maximum amount of solute under the solution conditions. If additional solute is added to a saturated solution, it will not dissolve. An unsaturated solution is holding less than the maximum amount of solute. If additional solute is added to an unsaturated solution, it will dissolve. A supersaturated solution is one holding more than the normal maximum amount of solute. This solute will normally precipitate from or come out of a supersaturated solution. So, the example I like to give here is making like sugar crystals. So, like that crystalline sugar candy that usually comes on a stick. My kids, I've tried to make this for them multiple times and I fail every time. I don't know if I just don't have the patience, if I'm not adding enough components to it, but I can't make that crystalline sugar on the stick. So my kids are like, you're a scientist. How are you not making this happen? I don't know. But basically, behind that, the sugar crystals, you would create a supersaturated solution. So you're going to boil water, and you're going to add sugar and add sugar and add sugar so that it is dissolved beyond its normal dissolving capacity. So typically, if you take sugar and you mix it into water, you'll be able to dissolve it even at room temperature. Now, if you've ever made Kool-Aid, in the old days, we didn't used to have like Kool-Aid squirters or water enhancers or anything like that. We used to just have a little packet of flavor and dump a ton of sugar into a big pitcher, and we'd mix it up, and then we'd create Kool-Aid that way. So making Kool-Aid that way, you know that if you add too much sugar, eventually the sugar won't dissolve in the water anymore. So it kind of settles down to the bottom. Well, if you keep adding more and more sugar, it's going to keep settling down unless you increase the temperature. When you increase the temperature of the liquid, like if you boil a liquid, it allows more sugar to be dissolved in the solution. Now, the goal for making the rock candy or that crystalline sugar candy is you're going to boil the water, you're going to add a lot of sugar, and you keep adding it until you create that supersaturated solution. Then you're going to provide an apparatus for the crystals to form on. So you typically put a little stick in there, or a string can be used. But then as the solution cools, crystals of sugar are going to come out of solution, and they're going to form on that string or that stick that you put in the solution. And over the course of several days, or maybe even a week, you will start to see the formation of a lot of crystals. So as that liquid temperature decreases and kind of stabilizes, anything that was above and beyond the normal amount of sugar that should have been in solution will come out of solution. And that's how rock candy or that crystalline sugar candy is formed. I really think it's my patience. I don't have patience for anything. If I don't get immediate results, I just throw it away. So I think if I let these systems sit for a little bit longer, maybe I'd eventually be able to make rock candy for my kids. So there's a bunch of calculations that come with talking about solutions. And these calculations are really important because if you're going to go work in the healthcare field, if you're going to have to make solutions to provide to patients, if you're going to have to dilute their medication in order to give to them, all these calculations are important. So the first one is mass percent. Mass percent is the number of grams of solute per 100 grams of solution. A solution with a concentration of 14% by mass contains 14 grams of solute per 100 grams of solution. To calculate mass percent, you divide the mass of the solute by the mass of solution and multiply by 100%. So calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of H2O. So to do this calculation, you're going to do the mass of the solute, which is 50 grams of sodium chloride, divided by the mass of the solution. Now this is the tricky part that students usually screw up on. We're not talking about the mass of the other substance. We're talking about the mass of the entire solution. The solution is the sodium chloride plus the water. So that's the 50 plus the 150. So that gives us 200 total. And then once we get our answer there, we're going to divide that by, or multiply that by 100%. So 50 divided by 200 gives us 0.25, and we multiply that by 100%, and we get 25%. So what's the mass percent? 25%. Calculate the mass percent in a solution prepared by dissolving 43.2 grams of lithium bromide in 153.2 grams of water. So go ahead and pause the video, work through this problem, and then we'll do it together. Okay, so mass of solute is 43.2 grams, and the mass of the solution is the 43.2 plus 153.2. So the mass of the whole solution, 43.2 plus 153.2, is 196.4. So that's what goes on the bottom here. Now we're going to do 43.2 divided by the 196.4, and we get 0.2, and we'll round that to 2. 21995.9, blah, blah, blah. We're going to round that to 0.22, and we're going to multiply that by 100%, and we get 22%. Calculate the mass of sodium carbonate and water needed to make 350 grams of a 12.3% solution. So this one's a little bit trickier. So we want to have a mass percent of 12.3%. So let's turn this into a decimal. So we've get 0.123. And we're going to set that equal to needed to make 350 grams of the solution. And actually, going through this problem is probably too challenging for the scope of this class. So instead of going through all of the instructions, we are going to skip this one. Specifying solution concentration through molarity. So molarity is defined as the number of moles of solute per liter of solution. The calculation is molarity is equal to moles of solute over liters of solution. Note that molarity is moles of solute per liter of solution, not liter of solvent. To make a solution of a specified molarity, usually put the solute into a flask and then add water to the desired volume of the solution. So how to prepare a 1 molar sodium chloride solution? First, you're going to add the solid, and then you're going to fill water up to the 1 liter point. So calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into a beaker and adding water to make 1.5 liters of sodium chloride. Given 15.5 grams and 1.5 liters, find molarity. So molarity equals moles over liters. So we have to ensure that the units that were given in the problem match moles and liters. First, we're given grams. This is going to have to be converted to moles. We're given liters. This one's good to go right in the equation. So let's tackle this first one. 15.5 grams of NaCl. We're going to convert that from grams to moles. 1 mole is equal to the calculated mass from the periodic table. So let me grab my periodic table. So sodium is 22.990. Chlorine is 35.453. We get 58.443. So we're going to multiply across the top, divide away the bottom, and we get 0.265 moles. Now we can put this information into the equation. M equals moles divided by the liters that's provided up here. And we get 0.177, and then the capital M for molarity. Calculate the molarity of a solution prepared by dissolving 9.35 moles of HBr in enough water to make 250 mils of solution. So go ahead and pause the video, try to work through this problem, and then we will work through it together. Okay, so moles of solute over liters of solution. We have this one in moles, but this one's in mils, so we have to convert that to liters before starting this. So 250 mils. We go mils to liters. 1 liter is 1,000 mils. So that becomes 0.250 liters. Now we can put it into the equation. 9.35 moles divided by 0.25 liters. 9.35 divided by 0.25, 37.4. And capital M. Calculate the molarity of a solution prepared by dissolving 1.02 grams of KCl in enough water to make 755 liters of solution. So again, pause the video, work through this, and then we will do this one together. All right, so we look at this. We know that this has to be converted to moles, and this is in liters, so that one's okay. So 1.02 grams of KCl, grams to moles. 1 mole is equal to the calculated mass in the periodic table. So potassium is 39.098. Chlorine is 35.453. And that gives us 74.551. Now we're going to multiply across the top, divide away the bottom. 1.02 divided by the 74.551 gives us 0.0137. So now we're going to put this into the equation. The moles, 0.0137 divided by the liters. And we get 0.0000181 molar. And then we will do this problem. So go ahead and pause the video and work through it. Okay, now in this problem, both of these have to be converted. So this has to be converted to moles, and this has to be converted to liters. So we have 73.2 grams to moles. We know 1 mole is equal to the calculated mass from the periodic table. So hydrogen is 1.008 plus chlorine is 35.453. We get 36.461 grams. Now we're going to multiply across the top, divide away the bottom. 73.2 divided by 36.461 gives us 2.01 grams, or moles, sorry. So now the second one, we have 29.02, or 2902 mils. We're going to put mils on the bottom, liters on the top. 1 liter is equal to 1,000 mils. So when we do this, 2902 divided by 1,000, we get 2.902 liters. So we're going to put this into the moles over liters calculation. 2.01 divided by 2.902, and we get 0.693. Okay, you can pause the video and work through this one. All right, so in order to go into the equation, this is going to have to be converted to moles. And this is going to have to be converted to liters. So after you do that, the correct answer is 0.5 moles. So now we're going to talk about the concentration of solutions. So a dilute solution contains a relatively small amount of dissolved solute. A concentrated solution contains a relatively large amount of solute. Hydrochloric acid is sold as a concentrated 12 molar solution. A dilute 0.1 molar solution is commonly found in labs. So solutions are often stored in concentrated forms called stock solutions. Many lab procedures call for less concentrated solutions, so chemists must dilute the stock solution to the required concentration. This is done by combining a certain amount of the stock solution with water. To determine how much of the stock solution to use, we use the dilution equation M1V1 equals M2V2. M is molarity, 1 is talking about the first solution. So we're talking about the molarity of the first solution. V is for volume, times the volume of the first solution. And we set that equal to the desired molarity of the resulting solution and the desired volume of the resulting solution. So the problem tells you to prepare 5 liters of a 1.5 molar potassium chloride solution from a 12 molar stock solution. So what we know is M1 is 12, M2 is 1.5, and V2 is 5. How do we know that? So when we read the problem, it says to prepare, this is what we want to end up with. We want a solution that has 5 liters and 1.5 molar. We're making it from this stock solution, so this is what we're starting with. So we know that this is our M1 because that is molarity. What we're preparing is our M2. And our requested volume is our V2. So what we're calculating is our V1. So we do M1 V1 equals M2 V2. M1 is 12. V1 we don't know, so I'm just going to put the letter X. And we're going to set that equal to our M2, 1.5, times our V2, which is 5. And now we're just going to solve for X. So 1.5 times 5 equals 7.5, so we have 12x equals 7.5. Now to isolate the x, we're going to divide by 12 on both sides. So that isolates the x there, and when we do 7.5 divided by 12, our V1 is 0.625 liters. How did we get liters? Well, we want to stick with the same unit that's provided to us in the problem. So if they provide liters, we're going to give the unit liters. So how to prepare this solution? we're going to take 0.625 liters of the stock and we're going to fill up water until we get to the 5-liter mark. In other words, since we're adding 0.625 liters of the stock, we're going to add 4.375 liters of water. That's how we would make that solution. And this is what's being shown here. So you're going to add the 0.625 liters of the stock, and then you're going to fill up the water to the 5-liter mark. How many milliliters of 12 molar hydrochloric acid are needed to make 500 mils of a 0.1 molar hydrochloric acid solution? Well, we want to make this. So what we want to make is our V2 and our M2. So this is our M1. Go ahead and do this calculation and then we will work through it together. All right, it's M1 V1 equals M2 V2. So 12 X equals 0.1 times 500. Now the units don't matter as long as they match, so we can use milliliters in this problem just fine. So 0.1 times 500 gives us 50. So we have 12x equals 50. Now to isolate the x, we're going to divide by 12 on both sides. We get 4.17 mils of the stock. So in order to make this solution, we are going to add 4.17 mils of the stock, and then we're going to fill water up to 500 mils total. So what is the molarity of the resulting solution when 300 mils of a 4 molar solution is diluted to 800 mils? So pause the video, try to figure this one out. It's a little bit different than what we've been doing so far, and then we'll work through this together. Okay, what is the molarity of the resulting solution? Means we're looking for M2. When 300 mils of a 0.4 molar solution, that's what we're starting with, V1 and M1, is diluted to 800 mils. This is our V2. So you have to read the cues from the problem to figure out what our numbers are. So when we started with 300 mils of a 0.4 molar solution, and we diluted it by adding a bunch of water, so now that is 800 mils, what is the resulting molarity? So we're going to just do our M1 V1 equals M2 V2. M1 is 0.4. V1 is 300 equals M2, we don't know, and our V2 is 800. So now we're going to do the 0.4 times 300. 120 equals 800x. Now to isolate the x, we're going to divide both sides by 800. we get 0.150 molar. Okay, we're going to work through this one, and then that'll be it for this lecture. So go ahead and pause the video and work through this, and then we'll do it together. Okay, you have an 8.9 molar solution, so that's what you're starting with, your M1. And you want to dilute it so that you have a solution, so your V1 or V2 and M2 are listed. What is the volume of the solute that you would have to use in this dilution? So it's looking for your V1. So we do M1 V1 equals M2 V2. We're going to do 8.9x because we don't know what our V1 is. We're going to set that equal to the 8.2 times 600. .2 times 600 is 4,920. Now to isolate the x, we're going to divide 8.9 on both sides. And we get 552.8, so we're going to round that to 553. So what's the volume that we would use? We would use 553 mils of the calcium chloride solution. Now from the previous problem, how much water would you add to create the total solution? Well, we want 600 mils total, so we would do 600 minus the 553 of the calcium chloride solution we're already adding, and we would only do, let me write this out for you. .47 mils of water would be added. 47 mils would be added.